If we want a computer to understand how to do something, we need to give it an algorithm.
Pick up brush.
Algorithm sounds like a big word, doesn't it? But actually, an algorithm is something very simple but important.
Pick up toothbrush.
An algorithm is a list of steps you give to computers to solve a problem or get something done.
Hi everyone, my name is Sahib. I hope by now you understand the basic concept of algorithm. Today, I and Ahmed would like to share with you the idea of a better version of insertion sort. As you all know, sorting is one of the most extensively studied aspects of computer science. There are several sorting algorithms such as bubble sort, insertion sort, selection sort, with each finding use based on the requirement and problem at the hand. Some are easier to implement than others, while others consume extra space. Some are more efficient when the data is almost sorted. In this presentation, we will be focusing on fast insertion sort, which is basically a derivative of insertion sort and improves the existing algorithm on both the time complexity as well as the number of comparisons. But first, let me give you a fundamental idea about insertion sort. Insertion sort is a comparison-based sorting algorithm. It is a simple iterative sorting procedure that incrementally builds the final sorted array. It is adaptive because it is efficient for data sets that are already substantially sorted with the time complexity of OKN when each element in the input is no more than k places away from its sorted position. Let me just uh, write that for you. Yeah. And then it is stable because it does not change the relative order of elements with equal keys, which means that the keys which have equal value in the unsorted array appear in the same order in the sorted array. It is an in-place algorithm as it only requires a constant amount of additional memory space because at a time only one element is being compared. It is an online algorithm. For those who don't know what an online algorithm means, it means that it is the algorithm that processes its input piece by piece in a serial fashion. Insertion sort considers one input element per iteration and produces a partial solution without considering the future elements. Now, let's look at the implementation of insertion sort. So now you can see the pseudocode on this presentation. Basically, the algorithm is premised on the idea that the left part of the array is already sorted. Values from the unsorted part are picked and placed at the correct position in the sorted part. This can be done as follows. At each iteration, the algorithm removes one element from the right position, finds its correct location within the sorted portion, and shifts each element after this location ahead by one position in order to make room for the new insertion. Its iterations repeat until all elements have been inserted. You can see the animation on your screen now. Now we will discuss the disadvantage of insertion sort. The drawback of insertion sort is that it does not perform as well as other algorithms. This is because it has a nested loop. As you can see in the pseudocode, it contains a while loop and a for loop. With n squared steps required for every n element to be sorted, the insertion sort does not deal well with the huge list. To overcome these drawbacks on the number of comparisons as well as the time complexity, we will now introduce to you the idea of fast insertion sort. Over to you, Ahmed.
Thanks, Saib. Now that we have a good understanding of insertion sort, its properties and drawbacks, let's focus our attention on fast insertion sort. Fast insertion sort improves on insertion sort in two major areas, the first being in the number of comparisons and the second being in the average case time complexity. The figure in this slide compares several algorithms based on insertion sort. At the top of the list is vanilla insertion sort, which has an average case time complexity and comparisons of in the order of n squared. Right below are algorithms like library sort and adaptive sort, which improves on certain metrics of insertion sort. For this presentation, however, we shall be focusing on fast insertion sort, the last three algorithms in this figure. They were developed in 2019 and they represent algorithms with O of n log n worst case comparisons, as well as O of n log n average case time complexity and constant space complexity. In this slide, we itemize some properties of fast insertion sort, also known as FIS. So FIS was inspired by insertion sort, where each element of the family achieves a worst case time complexity of in the order of n to the raised to the power of 1 plus 1 over h, where h is the degree of the array to be sorted. In the worst case, they perform O of n log n comparisons as opposed to O of n squared of insertion sort. And just like insertion sort, they are also adaptive, stable, and easy to implement. Here we discuss the implementation of fast insertion sort. The fast insertion sort function on the right takes two arguments. The first is the array to be sorted, denoted by capital letter A, and the second being the number of elements the array contains, which is n. We then calculate the degree h of the array, which is the log to base 2 of the number of elements in the array rounded up. We then, the k on line 3 is used to decide the length of the temporary array t. We use this array t to hold the values during insertion so we don't overwrite them. The algorithm from line 4 is based on an iterative cycle on the variable I. Just like in vanilla insertion sort, at the beginning of each iteration, the left portion of the array, beginning from index 0 to I minus 1, is assumed to be already sorted. Then, the algorithm sorts the element in block I to I plus k minus 1, which has the size of k, by calling fast insertion sort on line 6 recursively. And after doing this, we then insert all the elements of the block in the sorted portion of the array through the function insert block, which can be found at the left part of the slide. The overall number of iterations is then equal to n divided by k, where n is the number of elements in the array and k is the result of the expression on line 2 to the right of the slide. We round this number upwards to the next whole number. Coming to the left part of the slide, the insert block function on the left inserts block beginning from I to I plus k minus 1, which has a size of k, into the left side of the array beginning from 0 to I minus 1, which is the part of the array which is already sorted. This implementation uses the array t as an external space to store elements on the right block so that we do not overwrite them in the process of insertion. However, a drawback of the algorithm discussed in the previous slide is that it uses additional external memory of size O to the k because of the t array on line 3 of the previous slide that temporarily holds elements in the right block during insertion. This slide compares different strategies for the insertion of a sorted block of size k into the left part of the array beginning from 0 to k minus 1. This is the part of the array that is already sorted. So looking at this figure 5, we see that two blocks are involved. The working area W, which represents the block to be inserted, and a storage area S, which is used to temporarily store elements of the working area. In the first schema, A, an external storage T is used. This is consistent with the code explained in the previous slide. However, in schema B, the contiguous block beginning from I plus k to I plus 2k minus 1 is used as a storage area, while in schema C, we insert the block beginning from I plus k to I plus 2k minus 1, and the difference here is that here we use the middle block beginning from I to I plus k minus 1 as a storage area. So by removing the need for the external storage area T, we effectively turn the FIS algorithm in the previous slide into an in-place sorting algorithm, which makes it use less space and become more space efficient. In this slide, we compare the three FIS algorithms with some of the most efficient algorithms found in literature, such as merge sort, as well as several versions of quicksort. But in order to help distinguish the graphs more effectively, the graphs have been color-coded. The block insertion sort is represented by the color black, while the first and second variants of FIS are represented by red and beige, respectively. The standard quicksort is represented by a red dash. From the graphs, we see that the FIS algorithms show in all cases an O of n log n behavior in practice, outperforming the likes of merge sort and heap sort. These FIS algorithms also compare quite favorably against quicksort, even for large sizes of the input arrays. But where the FIS algorithms really shine relative to the other algorithms are for values of h, which is the degree, greater than or equal to 2 or less than or equal to 4. This means that the FIS algorithms perform excellently well with arrays with values that contain between 4 and 16 values. The recursive fast insertion sort is faster than the standard quicksort in almost all cases, and the performance difference turns out to be more evident for very small and very large arrays. Although not shown on the graph, the paper reported that while the reverse order arrays represent the quicksort worst case scenario, which is O of n squared time complexity, the FIS algorithms maintain their optimal O of n log n execution time, thus proving FIS algorithms to be among the fastest and most flexible general purpose sorting algorithms. To conclude, in this presentation we have discussed fast insertion sort, its origins, implementation, as well as its performance. We have seen from the previous slides that FIS not only significantly improves upon insertion sort, it also compares very favorably with mainstream sorting algorithms found in literature such as quicksort, merge sort, heap sort, even performing more optimally in most conditions. Because of its versatility and performance, we expect FIS algorithms to enjoy a wider acceptance amongst the academics and software engineers in the near future.